So today I'd like to tell you something about, we heard something about rigidity. I would like to tell you something about maybe the opposite notion, namely mobility. And I will report about the recent work with Josef Schicho here in Linz. So let me introduce the objects we will be dealing with. And so a multipod is a mechanism, a mechanical device, which is constituted of two rigid bodies. They are called the base and the platform. And these two rigid bodies are connected by several other rigid bodies, which you can think about them as rods, which are called legs. And the legs are anchored at both the base and the platform via spherical joints, namely joints that allow any possible rotation around them. In the picture, what you're seeing here is what is called a planar pentapod. So it's planar because the base and the platform anchor points lie on a plane, and it's a pentapod because it has 5 legs. So please notice that we don't restrict ourselves to planar mechanical devices. These are also called parallel manipulators, but the anchor points may be displaced in space. So they can define truly 3D configurations. So what we would like to study is the notion of mobility for multipods, and just so for planar mechanisms. The reason why we would like to understand mobility, which is the possibility for the mechanism to move, so that the platform moves even if we keep the base fixed. And so the reason why we would like to understand clearly mobility is that often this is an undesired behavior, because often people would like to steer the platform, for example, by modifying the length of the legs. And if a manipulator exhibits mobility, this means that we don't have control anymore on the position of the platform, just by operating on the legs. So the way how we encode realizations in order to speak about mobility is the following. So given a configuration of our multipod, we can consider the direct isometry that sends the actual configuration into a prescribed, let's say, initial configuration. Okay, so in this way, every configuration is determined by a direct isometry. So this is one of many possible ways of encoding a configuration of the pod. And another way could be, for example, storing the positions of all the platform points. Okay, but you will soon see why we like this way of encoding configurations. So given a multipod, we can speak of its configuration space. So the configuration space is the subspace of the group of direct isometries, so which we denote by SE3. So it's a subset of the configurations that can be reached by a manipulator. So each leg, as you now see, imposes conditions on the group of isometries, because the more legs I impose, the more constrained is my multipod. And since the group of direct isometries is 6-dimensional, because we have a 3-dimensional part of rotation together with a 3-dimensional part of translations, then we can expect the following behavior, namely that if we have a general pentapod, so a 5-pod, then we expect that this object should exhibit 1 degree of freedom. If we have instead a general hexapod, so a parallel manipulator with 6 legs, then we expect 0 degrees of freedom. So we expect that the manipulator is rigid. Okay, and in fact, this is actually true, and one can prove that the possible number of configurations is 40 in this case. So you see that hexapods are interesting because they are at the interface between mobility and rigidity. And studying hexapods is extremely interesting. Is one of the topics I have been studying together with my co-authors. But why stop there? So then, in general, one may ask, okay, how many legs can we add to a manipulator so that it's still mobile? Okay. And then there are two possible scenarios. Either we can add infinitely many legs, or we are allowed to add finitely many legs. And this is a curious case. The second, I believe, is that one shows that you can actually add at most 20 of such legs. And this is the case of icosapods. But today, we are not concerned about the second scenario. We are rather concerned about the first scenario. So namely, when we have infinitely many legs. And actually, what I would like to tell you about is a construction of a mechanism which is both mobile and admits infinitely many legs. There have been already known mechanisms that have infinitely many legs, but from what we can tell, the mechanism that I will discuss with you today is new. Actually, maybe rather than the result, which I believe is interesting, the main object of study that I would like to discuss today is the technique that we adopted, and it is a technique that involves defining both compactifications for the space of legs and of configurations of a pod, and a technique that involves a duality between these two objects, namely between configurations and legs. So let me start with discussing compactifications. And please interrupt me at any time if anything is not clear, if you have any question. So the idea is that we would like to provide a particular model for the group of direct isometries of R3. So a direct isometry, of a free space, it can be described as it is in the slide as a map that sends a vector point V in R3 to the point m times b plus y, where m is an orthogonal matrix and y is a translational vector. So what we decide to do is to encode an isometry not only with the matrix M and the translation vector Y, but rather we add some other quantities. So first of all, we add another vector X, which is obtained from Y by applying to Y the transpose of M and taking the opposite. And then we encode the scalar product of the translational vector with itself. So you see this variable R encodes the scalar product with X to itself, which is the same thing as a scalar product with Y to itself. And then we decide to consider this as a point in projective space where we have, if you count them, 16 coordinates, counting a homogenization coordinate, which we will call H. And due to the definition, to the construction, or to the definition of these quantities, you see that they satisfy the following equations. Namely, at first you see that M is orthogonal, so once multiplied with its transpose, it gives the identity. Its determinant is non-zero, and then you see just the homogenized versions of the definitions of the quantities X and R. Then if you take the Zariski closure of the object that you obtain, because here we had that the quantity H is non-zero, but then you can take the Zariski closure, what you get is a variety X, which has dimension 6, which is expected because it comes from a group of dimension 6, and it has degree 40. This variety contains a copy of SE3 and sits inside P16. So why did we choose such a weight, such a model for the group of isometries? The reason is the following. So suppose you take a leg, which is namely described by a platform point A, a base point B, and their distance, so the length of a leg, which we call D. Then the condition imposed on the isometries, which please recall, they codify the possible configurations. So on the space of possible configurations, we impose that an isometry sigma is compatible with the leg if the distance between B and the point that is obtained from A once you apply sigma stays D, because this means that the isometry does not change the length of the leg, which is what we want. Then, if we rewrite this condition in the coordinates of P16 that I just introduced, what we find is that the condition looks like as shown. And in particular, what you see is that this condition is linear in the blue coordinates, which are the coordinates of the of SE3, so the coordinates of the configurations. Okay, so the reason why we chose this compactification is that in this way the conditions given by the legs become linear. And then you see that you can recover the result that we had before, namely that we said that a general hexapod has 40 configuration. Why is it the case? Because a general hexapod determines 6 general linear equations, and the variety X that compactifies SE3, we said has degree 40 and has dimension 6. So when such a variety intersects these linear equations, it intersects within the linear space that we define into finitely many points, and the number of points is equal to the degree of the variety, which is exactly 40. But then we can do a little bit better, and actually this will be crucial in our discussion. So we can even improve the shape, so to say, of the equation, of the condition, sorry, determined by a leg as follows. So if you look at the condition, so you see that the homogenizing variable h multiplies a quantity which is a scalar a plus b scalar b minus b squared. Okay, we get rid of this quantity by calling it with a different name. We call it L. And then what we see is that if we take the base and the platform points, and instead of thinking of them just as points in R3, we consider them as points in P3 by attaching to their coordinates a homogeneous coordinate which has the value of 1. Then we have a pair of points in P3, and there is a well-known construction in algebraic geometry that allows to associate to any pair of points in P3, so to a point in P3 times P3, a point in P15. So this is the so-called Seger embedding, and very concretely, the map that goes from P3 to P3 to P15 is the one which is given by the condition that Zij, namely the coordinates in P15, are just given by the products of the coordinates in P3 times P3, namely Zij is equal to Ai times Pj. So once we make this substitution and we rewrite the condition that we had before, we obtain a condition which is now bilinear in both the variables determining the configurations, so namely the variables h, r, x, y, and mij, and in the coordinates determining the legs, which are the coordinates z, zij, and l. Okay. So we call this the so-called spherical or sphere bilinear condition. This is the the condition that is imposed by the presence of a leg. And this will be one, maybe the key gadget, the key tool that we will be using in this talk. So why is this so important? Because this allows to, so this condition allows to define a duality between two projective spaces. One is the projective space that we already encountered, namely the P16, where the group of isometries lies, okay? And then we have the P16 whose coordinates are L and Zij, okay? And in this P16, there is a variety which parameterizes all possible legs, okay? So this variety, which we denote Y, is the cone over the image of P3 times P3, because what we encode are the 2 points, the base and the platform points, and their distance, okay? So then the previous, this bilinear equation determines a duality between these two projective spaces. And this duality, which algebraically is a trivial duality, because if you look at it, this is just a diagonal matrix, okay, which has ones and minus twos on the diagonal. But by interpreting it as a duality between these two special spaces, we get something very nice, namely that if we fix a locus of isometries, okay, and we take its span and the dual under the bilinear equation that I described you, and I intersect this dual with the space of possible legs, what I obtain is the locus of legs that are compatible with my given locus of isometries. And vice versa, if I start from a locus of legs, and then I take its span, I compute its dual, and I intersect it with the variety X, what I get is the locus of isometries that are compatible with the legs that I prescribed at the beginning. Okay, so this duality plays very well between the isometries, the space of configurations, and the space of legs. Okay, and that is the main property that we are going to use in the constructions and this talk. So maybe this is the most important slide in the whole talk, because it describes the key property of this duality. So if you have any question, please feel free to ask me, because
can you describe the locus?
Sorry?
Can you describe the locus in more detail?
Which locus? So because the idea is that you fix a locus. So for example, you fix a locus of isometries, namely you fix, for example, a curve of isometries, namely a curve of configurations. And then by computing the dual, what you get is the space of legs that are compatible with those configurations. Okay, and this locus can be empty, or can be infinitely many points, can be one-dimensional or higher dimensional. Okay, is this what you were asking?
Well, the locus constraining the locations of the legs, right?
Yes, the locus of legs that are compatible with, for example, the given configurations.
So you're limiting where the legs can be.
Yes, but not by, yes, but I limit that by fixing the configurations that I want to achieve.
Right, okay.
And vice versa. I can fix the legs and then check which configurations they achieve. Okay, maybe this is a little bit more natural way of viewing this duality, but of course you can go both ways, and we will be going both ways.
Okay, thanks.
You're welcome. Any other question? Okay, let's play. So before going to the main construction of this talk, I would like to start with a warm-up. And the warm-up is about a well-known, a very well-known result by Duporc that says the following: that if we have a mobile planar pentapod, then we can add a leg to this pentapod without changing its mobility. Okay? And so I would like to discuss this statement in the light of the framework that I introduced so far. So I will, so there is actually a lot to say about this result, and there is a nice paper by Georg Navratil about that. So I will be on purpose not fully precise, namely, I will not address all extremal cases that can happen, but I will limit myself to a general case because this is just a toy example. So if you are interested in a more thorough discussion, I refer you to the paper by Georg Navratil. So let's try to cast this situation into our framework. So since we here in this case we talk about planar pentapods, let's specialize to a planar setting. So namely, inside the variety parametrizing legs, I consider only the variety parametrizing planar legs. Okay, and this is obtained, we call this variety YP of planar, and it is obtained by intersecting our cone Y of all legs with a special linear space. And what you get is that this YP is of dimension 5 and of degree 6, is a variety of dimension 5 and of degree 6. So then we can restrict the bilinear sphere equation that I had before to the space where YP lives. Okay, so this is a smaller space. Okay, and then once you restrict it, you obtain the equation that I showed you before. Sorry, that I showed you here in the slide. And then what you can do is that you can consider what's the dual space in terms of configurations. And what you get is that the dual space in terms of configurations is a quotient of the is a projection, sorry, of the P16 onto the coordinates. Essentially, we forget the coordinates that have a 3 in their index. So you see we have only M1, 2, 1, 1, 1, 2, 2, 1, 2, 2, and then we have X1, X2, but not X3 and not Y3. Okay. And so by projecting X on these coordinates, we get a variety which is called XP, and this has dimension 6 and degree 20. And now we start playing our game. Now, so okay, so we said that we start with a pentapod, so we have 5 legs. So we have 5 legs. These 5 legs determine P4, the span P4. Okay. Then now the setting now lives in a P9. Okay, so then we can consider the dual of this P4 into the P9. So the original P4 lives in the P9 containing YP, so in the leg P9, and then its dual is in the configuration P9. Okay, and its dual, if you do the computation, is also P4. Okay, now we have a P4 in a P9, and in P9 there is this variety XP, which has dimension 6. Well, then this means that this P4 will intersect this variety XP in a curve. And here we rediscover what we already know, namely that a planar pentapod, and in general actually any pentapod, is mobile because the space of configurations is a curve. Okay, very good. But then now we can look back and see that the only thing that mattered to get a curve was the initial P4. Okay, so the span of the 5 points. But the P4 in P9 intersects YP, which is a variety of dimension 5, into finitely many points. How many? The degree of YP. But the degree of YP is 6. which means that the P4 that was spanned by the initial 5 points, the initial 5 legs, actually intersects YP in a further 6th point. Okay, and so in this way we got the 6th leg for free. Then by adding this 6th leg, we don't change the locus of possible of compatible configurations, because the dual is the same, because we haven't changed the P4 we started with. Okay, so this is the toy model, I would say, where you can see how you can use this duality to go back and forth between legs and configurations, and see how you can play with them. Okay, and any questions so far about this? Okay, so if not, I would like now to go to the core part of this talk, with which I will conclude, and namely to show you how we can construct such a new mobile infinity pod. So first of all, we will constrain its possible configurations. So we will not consider any possible configuration of pods, but we will consider a special subvariety of the variety X, which we call X-inv. And this is the subvariety of involutions in SE3. So SE3, again, is the group of direct isometries in R3. Involutions are rotations by 180 degrees around a fixed axis. And one can consider only those configurations that are given by involutions. So in terms of the coordinates that we introduced before, an involution is determined by imposing that the matrix M is symmetric, so you see M equals to MT, and the two vectors X and Y are equal, so the vector X equals to the vector Y. So the variety we obtain is a 4-dimensional variety, which we call X-inv. Now, what do we do? So this X-inv lives in a P10. Okay, so it lives in a P10, probably defined by the equations M equals M transpose and X equal to Y. And now, if we change a little bit the varieties in leg space, so namely we introduce these quantities Sij, which are the sum of Zij and Zji, we get another duality that now fits well with the setting that we introduced here, the setting of dualities, of involutions. Namely, if I consider the P10 where the space of involution lives, and then I consider this, the duality, the bilinear form that I show you here, this determines a duality between the set of involutions and a particular quotient of the set of legs, which is given by identifying legs that are obtained by swapping base and platform point. So this means that if I identify the two legs given by AB and BA, what I get is still a variety of dimension 7, but the degree gets cut by half. And it's the image of the map that I showed you here in the picture. So this means that in this setting, X-inv and Y-inv play dual roles via the duality that I define here, in the same way as X and Y play dual roles with the initial duality. Namely, that the duality specifies me and can be used to compute which configurations are compatible with which legs, with which pairs of legs in this case. Okay, so what is the main idea of our construction? The main idea is that we start from the configuration curve this time. So before we started from the 5 legs, right, of the pentapod. In this case, we start with the configuration curve, and it will be a curve in X-inv, and we will construct it so that it spans a P5. Why? Because if the configuration curve spans a P5, then the dual will be a P4. And if I have a P4 in leg space, which is a P10, okay, I have a P4 in a P10 where Y-inv is a variety of dimension 7, which means that this P4 will intersect Y-inv in a curve. Okay, so which means that what we get is an object which has infinitely many configurations, which means that it is mobile, and allows infinitely many legs, which means that it is an infinity pod. Okay, so in this way, we would have constructed an infinity pod, a mobile infinity pod. Okay, so the whole point is to construct properly the configuration curve. And to explain and to do so, I'm going I need to tell you something, some more constructions to say before. So, so far we consider the isometries, you know, as a whole, roto translations, but we can focus ourselves on the rotational part, which is in the coordinates that we introduced, determined by the m and h coordinates. Okay. So if I project my variety x onto these coordinates, what I get is a variety this parameterizing only rotations, which we call, for example, x rot. One then sees that this x rot is nothing but the so-called Veronese embedding of P3 into P9 up to a change of variables. So this is nothing but an embedding of P3 into P9. Which means that we can rewrite rotations in terms of 4 coordinates, the E coordinates. And this is a well-known theorem by Euler. So these are called the Euler variables, the Euler coordinates for rotations. Okay. So then by using the E variables to encode rotations and two other kind of quantities, we can give another model for the space of involutions. So with these two other quantities that we introduce, instead of using x and y, I use their sum and their difference. And in this way, I define the quantities pi's and qi. Okay. Then one needs to do a little bit of computations and to see how things work properly. But what you can see is that you can get another model for involutions after x-inv, which is given by z-inv. And z-inv is a variety that lives in a weighted projective space. I will not talk about that because essentially we will not need that. Where coordinates are the E coordinates without E0. So the coordinates we will use are just E1, E2, E3. And then the P coordinates, because the Q coordinates will be 0. Okay. This is just another model for involutions, but this will allow us to describe the configuration curve in an easier way. So how do we construct our configuration curve? We do as follows. So we start from a planar curve, okay? Because recall we should not use the variable E0. So essentially we set E0 to 0, and then what we get is a planar curve in P3. What we want to construct is a map from this planar curve into Z-inv, which is essentially an embedding of this planar curve. So Z-inv has the E coordinates, so we will just use the E coordinates of the planar curve. The Q coordinates are 0, but we need to determine the P coordinates, okay? And the P coordinate, namely, we need to determine 3 polynomials, capital P1, capital P2, capital P3, that are polynomials in the EI coordinates, because they are polynomials on C, which give them up from C to Z-inv. And due to the definition of Z-inv, you see that there is this equation that must hold. Then what these polynomials must satisfy is that EI times P1, E1 times P1 plus E2 times P2 plus E3 times P3 must be 0. Which means that these polynomials Pi must be syzygies of the vector E1, E2, E3. So they should look as depicted in the at the end of the slide, where L1, L2, L3 are linear forms, linear polynomials into the EI coordinates. But then, once we now constructed this this map, we need to then lift this map to the original XINV. Okay, and in order to do so, essentially we have the E coordinates for which it is easy to construct the MIJ coordinates, and from the P and Q coordinates is easy to construct the X and Y coordinates. So what is left is the R coordinate. Okay, so we recall in our model we have the MIJ coordinates, the X coordinate, the Y coordinate, and the R coordinate. The R coordinate was the coordinate that encoded the scalar product of the translation vector with itself. So it satisfies an equation of the form HR equals X scalar X. Okay. Now, with what we know, the R coordinate must satisfy the equation that I showed you there, namely that the sum of squares of the EIs times R equals a fourth. This is just a constant times the sum of squares of the polynomials PIs. Okay. But we should take into account that if we want to construct a configuration space, not just an arbitrary curve in XINV, but really a configuration space, namely something that really comes from legs, then we should look at the equations determined by legs, which has the shape that I reported here, from which we see that the R variable depends linearly on the other variables. And from this, we see that in the previous equation, we must have that, sorry, I wrote it in the opposite order, that the sum of squares of the PIs divides the sum of squares of the EIs. Okay, so once you take all of these into account, you can devise an algorithm that provides you with a correct configuration space whose dual really gives you a curve in the leg space, namely allows you to construct a mobile infinity pod. Now, one of the reasons why I wanted to discuss with you about this topic is that everything here works out of the complex numbers. But then one can ask ourselves, okay, how can we devise our curve so that all the construction actually is real? So namely, I really get infinitely many real legs. And I believe that this is a nice and interesting question that can be asked here in this case, and for many other situations where we have a lot or maybe some information about configuration curves, but we would like to construct the corresponding pods. Namely, we need to have a real construction of these objects. And so I hope maybe this could interest any of you, and in order to think about this question in terms now of the reality of the solutions. Okay, I think my time is over. Thanks a lot, and if you have any question, I'm happy to answer, or you can contact me at any time. Thank you very much.
Thank you very much for the nice talk, Matteo. So maybe we can take one quick question if there are, and then postpone the rest of the questions to the break.